Hi everyone, this is Amir Muhammad Shahsawarani. Now we're going to our next step, our final theoretical session in this very beginning course about our algorithms. Now, after speaking about many introductory issues, the final part of this course, the session 4 of the theoretical issues are about pillars of algorithmic issues in our programming system. As we delve into the realm of algorithms, it's essential to understand the fundamental principles and concepts that govern this field. As you know, in computer science, algorithms are the foundation upon which software is built, and a solid grasp of these pillars is crucial for any aspiring programmer or computer scientist as well. So let's explore these basic principles and concepts that underlie algorithmic thinking. We have divided them into 8 categories and we call them 8 pillars. Maybe you found somewhere else more than this or less than this. It is combined. I'm not sure, but let's move on. Okay. First of all, pillar 1 is efficiency. Efficiency is the cornerstone of algorithm design. A well-designed algorithm should be able to process input data in a quick manner, we can say quick input, using minimal resources such as memory and processing power. This pillar is concerned with the time and space complexity of an algorithm, which determines its scalability and usability in real-world applications. Key concepts of in this pillar, in this category, would be, first of all, time complexity, the amount of time an algorithm takes to complete, which typically measured by the number of operations performed, or maybe some other issues, I'm not sure. The second one, space complexity. When we speak about space complexity, we mean the amount of memory required by an algorithm. We exactly mean the physical space it takes, usually measured in terms of the maximum number of variables or data structures used for an algorithm. Second, so for the third one, big O notation. When we speak about this issue, a mathematical expression would consider mind that describes the upper bound of an algorithm's time and space complexity. It's a sort of combination of two previous key concepts. Okay, our next pillar, it's correctness. Correctness is the guarantee that an algorithm produces the correct output for a given input. This pillar emphasizes the importance of verifying the correctness of an algorithm, ensuring it behaves as intended and avoids errors or bugs. So it would be to some extent alike some issues of validity we call in psychometrics. So the key concepts of correctness would be algorithmic correctness. It's the property of an algorithm producing accurate results of all possible inputs. The second one is formal verification. Formal verification is a process used to mathematically prove the correctness of an algorithm with the use of formal methods and techniques. The third one in the pillar in the category of correctness would be test cases, a set of sample input output pairs used to test and validate an algorithm's behavior. We may have some tables, we call it trace tables, and we will see it from the next session on in our pseudocodes that we shall use them so that we can understand the correctness of our codes in the form of algorithms. Our next pillar, the third pillar, is universality or universality. Pardon about my accent, I'm not sure about perfect English accents. Universality refers to the ability of an algorithm to handle a wide range of inputs, including edge cases and unusual data. This pillar, this category highlights the importance of designing algorithms that are robust, flexible, and adaptable to varying input conditions. We mean that every odd condition shall be handled in our algorithm if it is defined by the algorithm. So, the key concepts in universality algorithm issue of concern would be first, input validation. When we speak about input validation, we mean the process of verifying the validity and integrity of input data before processing it. Uh, I'm just meaning that the correct input issue, for example, how can I say in our real world, if we are using a vending machine which works in Germany, for example, we shall put in euro currencies, but being in Japan, we shall put in yen currencies. Uh, I think it would be a sort of, you know, maybe 50-50 okay for input validation. We can say example instance. The next one is error handling. Error handling are techniques used to detect and recover from errors or expectations during algorithm executions. Uh, if you have coded before, and I think you have done it, we have the blocks of try and catch. This points out the try and catch blocks. Edge cases, unusual or boundary, oops, unusual or boundary inputs that can reveal flaws in an algorithm's design or implementation would be edge cases. These edge cases are of much concern because it shall be understood, it shall be tested, and bug fixation. I think depends most of is valuability. It's on this case of edge cases. Okay, the fourth pillar, composability. Composability is the ability to combine multiple algorithms to create a new, more powerful algorithm. So this pillar puts its emphasis on the importance of designing algorithms that can be easily composed and extended to solve larger problems. So it's obvious. I don't think it needs more explanation. The concepts we do have here, first of all, algorithmic composition, the process of combining multiple algorithms to create a new algorithm with the algorithmic composition. Modularity is the second one, second key concept in composability, which concerns the design principle of breaking down complex algorithms into smaller independent components. uh, we can say it's exactly vice versa of the first concept, algorithmic composition. Okay, the down scaling, it's algorithmic composition would be said, I think, or it's a sort of upscaling, mixing up together, composition, decomposition, maybe we can say, and function abstraction. Function abstraction is a programming technique used to encapsulate functionality and facilitate composability. Uh, it's, I think, the same that we have in our fourth pillar in object-oriented programming and object-oriented design. It's exactly that abstraction. Good. Our fifth pillar, our fifth category, adaptability. Speaking about adaptability, adaptability is concerned and convinced the ability of an algorithm to adjust to changing input conditions or requirements. This category, this pillar, highlights the importance of designing algorithms that can adapt to new information, learn from experience, and or evolve over time. We would make use of it more and more in our AI implementations nowadays. Good. First, we want to speak about dynamic programming. In dynamic programming, it's a sort of technique used to solve problems by breaking them down into smaller subproblems and combining their solutions. We have done it, I think, in our high school, in algorithm and algebra, mathematical issues. I'm not sure if you have had these courses in your high schools, but in Iran we do have it. Okay, the next key concept is meta algorithms. Meta algorithms are algorithms that create or modify other algorithms. Some have said about these issues, I have remember God algorithms or something like this, allowing these meta algorithms, allowing for adaptation and learning for us. The third key concept here, reinforcement learning. Reinforcement learning is exactly a machine learning approach used to train algorithms through trial and error interactions with an environment. These learning reinforcement techniques are mostly useful nowadays in our working AI systems with which we do no sort of guidance provided to the algorithm. Uh, the algorithm flies solo and does it everything it needs in its own. Good. Our sixth pillar, our sixth category, scalability. Scalability is the ability of an algorithm to handle larger input sizes or increase processing requirements. This pillar, the scalability, puts emphasis on the importance of designing algorithms that can efficiently process and analyze large data sets even as they grow in size. So, in this manner, we do have some key concepts. First of all, data structures. The organization and managing of data within a program would be categorized in data structures. The second key concept, algorithmic parallelism, uh, it points out and refers to techniques used to execute multiple tasks concurrently, simultaneously, at the same time, taking advantage of multi-core processors or distributed computing environment. We have seen it in multi-thread issues, and we will practice it in next few sessions, I think, if it would be applicable in our just introductory course. If not, we would do it for sure in our advanced algorithm course. Okay, the third key concept in this pillar, the fixed category of scalability, is distributed algorithms. Distributed algorithms refer to algorithms which design for execution on multiple machines or nodes. These sorts of algorithms, distributed algorithms, often used in cloud computing or grid computing settings. For example, something like Azure Cloud. I'm not sure if I spelled it right or wrong. Azure, the technology of Microsoft. Good. Okay. Our seventh pillar, our seventh category is robustness. Robustness is the ability of an algorithm to withstand errors, exceptions, and unexpected input conditions. This category highlights the importance of designing algorithms that are fault tolerant and resilient to failures and anomalies. As I've just told you earlier in this video, we do have some God mode formula. We call it try and catch block. Okay, everything, the exceptions. In this manner, we do have some key concepts. First of all, error detection techniques. Error detection techniques are used to identify and detect errors or exceptions, during algorithm executions. We just think of try and catch block. I'm not sure if you do so, but my mind obsessionally puts emphasis on this. Exception handling, the process of catching and handling exceptions in a program, ensuring robustness and reliability, is called the exception handling. Most of us have experienced these try and catch blocks, but telling you the truth, it's not good to use try and catch blocks. It's just a shortcut to only show that our program works and we don't have any sort of bug or blockade in our running program. But it's better to handle all these exceptions, exception management and exception handling in some classes, in some files, in some settings, and we can make some abstraction and encapsulation for it that we would talk about it later in some other videos. This third one here, fault tolerance. Fault tolerance is the ability of an algorithm to continue functioning despite the presence of faults or errors. Okay? The last pillar, the last category. When we just use pillar, we mean to make some imagery for you about mansions or some halls, great halls of ancient uh, buildings that have many pillars, uh, within themselves. You just can name each pillar, and it would help you better remembering them. Our last but not least important pillar is human factors. When we speak about human factors, we just want to refer to the psychological, social, and cognitive aspects of algorithm design. I mean, just my profession. This pillar, the human factor pillar, emphasizes the importance of considering human perspectives, biases, and limitations when designing algorithms. Tell you the truth, I've just spoken with Llama 3, 8B, 8 billion parameters of Meta AI. I've just asked it if it is man or woman, male or female, or it uses uh, female protocols, female system of thinking, or male system of thinking, and it's just answered me. It has no gender or sex, and it has been made up of uh, all men and women together, so that it would be a, you know, better algorithm than just being a man or woman. Okay, closing the parenthesis. Key concepts in our human factors. First, user-centered design. User-centered design is a design approach that prioritizes user needs, goals, and behaviors with tailoring the design so that our user would be more comfortable. We call it user-friendly. And you have seen this issue uh, is become a domain that we call it UX, user experience. Hmm? Third, cognitive psychology, the study of mental processes, perceptions, attention, decision making, we call it executive functioning, to inform algorithmic design. Hmm? My profession? Yes, I shall promote myself somewhere. And the third one, social factors, my second PhD, the impact of social norms, cultural influences, and group dynamics on human behavior and algorithmic design, all are put together in social factors. We shall think about them, we shall use them, we shall implement them in our uh, algorithm of programming issues. So thank you coming with me. These pillars of algorithms, it's I think better call it in plural form, provide a comprehensive framework for understanding the fundamental principles and concepts that underlie this field. By grasping these essential ideas, you would be better equipped to design, to analyze, and to implement algorithms that are correct, that efficient, that universal, composable, adaptable, scalable, robust, and considerate of human factors. So all these facets are all categories. As you navigate the world of algorithms, remember that mastering these pillars will enable you to tackle a wide range of problems and create innovative solutions that make a lasting impact. That are saying that algorithms in computer programming help you to be some sort of a programming architect. Hmm. Join me on this fascinating journey as we explore the depth of algorithmic thinking. And from next video, I think we would better start some pseudocoding to make some active and in action videos. Thank you, everyone. Bye for now.